All right, so we start with the need for lightweight cryptography. So in this introductory talk, I will try to explain what is lightweight cryptography and why we need it. But in order to talk about lightweight cryptography and its implications to Internet of Things, first we need to agree on what Internet of Things is, okay? So this term is actually not very well defined. You cannot find a single correct definition. This is why I actually focus on NIST's document, Network of Things. And actually they use the term Network of Things instead of Internet of Things because most of the time these devices are connected to a network but not to the internet. But anyway, so the picture taken from this NIST document is as follows. They say that we have sensors, okay? Many sensors scattered around. And these sensors are grouped together and they are called clusters. So here C1, C2, etc. are clusters. And these are connected to an aggregator. By connection, I mean they communicate with each other. So for instance, these sensors gather some data and send it to the aggregator. Sometimes these small aggregators send it to a bigger device or something. And this part is called e-utility, okay? So actually, sometimes they send it to the computer, these results, these aggregators. And depending on those results, the aggregators may tell sensors to do something else. For instance, here's a simple if statement. If, for instance, the sum output of the function is larger than 200, set wing flaps to 10 degrees, etc. Okay, and with the computer, you can, modify these aggregators, send some commands, and so on. So this is the picture of Network of Things from NIST. Because if you only focus this part, sensor networks are around for years, so you don't need to give it a new name, right? And this is why we have to focus on all of these subjects. So it has some different devices. For instance, these sensors are generally very small devices. They have limited capabilities in terms of CPU and memory. But all of these devices communicate with each other. So here, security becomes an important, and you have to make sure that they communicate in a secure way. So you should provide encryption, but you should also provide authentication, because we can put some fake sensors here, send fake data, and so on. Okay, so in the industry, in factories, most of the time this communication is not encrypted. So for this reason, if you can get access to the network of the factory, then you can, modify, send false commands to these devices, and actually you can cause harms. Stuxnet virus is one of an example to this. In that example, they modified the centrifuges in Natanz nuclear center, nuclear plant in Iran. So after some point on, they reduced the RPM of the centrifuges so that it becomes broken. So this is a huge problem in factories. So industrial Internet of Things is another topic. And again, there is almost no encryption at all in those places. And the main problem with the Internet of Things, we don't know who is responsible for security, okay? Because once you produce a device for the Internet of Things, so should the factory who produces that device be responsible for the security, or the company who is selling it is responsible, or the software developers should be responsible for it? We don't know. There is no regulation for that, so nobody puts any security in it. So most of the IoT devices come with no security at all. Okay, this is one of the main problems, because if you want to, harden the security, then the device costs increases, so it becomes more expensive. To avoid this, people don't put any security at all. So this is one of the problems, and this is where lightweight cryptography comes into play. Because as you can see from the previous picture, we need encrypted communication, we need security. So this is why we need cryptography. But you might say that, okay, we already have modern algorithms that work on computers, are on our mobile phones, so we can use the same on these devices. And here, the problem is that these small devices may not be capable of running those algorithms. Okay, so we are not only interested in security, we are also interested in authenticated encryption. So, data authentication and user authentication. But we are also interested in battery life, because most of these devices run on battery. So if you put an algorithm that will consume too much power, then the device battery will deplete faster, right? So you should come up with an encryption algorithm that is battery friendly. Another thing you consider is energy. Another thing is latency, because you might have a good algorithm, but by latency, we mean that the time it takes from when you start the encryption process and produce the cipher text. Okay, if it is too long, then it may not be suitable for you. For instance, in this picture, most probably the sensor will send data to these aggregators maybe once every second. So your encryption should be fast enough, so the latency should be less than 1 second. Okay. As in some cases, maybe they send data in microseconds, and so depends on the application. All right. Another thing is throughput. In some cases, we don't require too much throughput, but if these sensors are sending huge amounts of data, then you need an algorithm that encrypts, provides encryption so that it provides large amounts of megabytes or gigabytes per second of encryption. Okay, so throughput is another consideration. And finally, side channel resistance. So maybe it is the last, but maybe it is the most important part here. So a lot of people who work in computer science or security doesn't know anything about side channel attacks or side channel resistance. Here, the problem is as follows. In our computers, we are using algorithms, protocols that we believe that it is secure. For instance, for encryption, we have advanced encryption standard, AES. So we use it, for instance, in this Zoom session, my video and voice is encrypted using AES 256 in the GCM mode, which we'll be talking about in the following weeks. And we believe that this algorithm is secure because in the last 20 years, we couldn't break it, okay? But the thing is that if you take that algorithm and put it into this sensor, and somehow if that sensor is capable of running it, we can break it. So it becomes a huge question mark, because if it works correctly on a computer or on my mobile phone, why it becomes broken in a small device, right? Here, actually, this is where the side channel analysis comes from. Here, you don't break the algorithm itself, you break the physical implementation. For instance, there are some attack techniques. Since these devices are small, and sometimes we can physically reach those devices because the sensors are scattered around maybe. So for instance, maybe you cannot open it inside this device and look at the secret key, but you can just put two cables and measure how many power it consumes, okay? And plot a graph. And just by looking at the graph, you can understand where it performs big operations and small operations. And just by looking at it, actually, you can understand where it is performing multiplication and when it is performing addition. And just by looking at these operations, you can actually determine, for instance, if it is using RSA, you can determine if the RSA secret key bit is 0 or 1 just by looking at the plot of the graph of power usage. Okay, you cannot do it to your CPU because it is not that easy. You cannot understand how much power it consumes. But for a very small device like this, you can just look at the power consumption and understand what operations they are using. Another way is looking at the timing. You can check the timing of operations and break it again, and so on and so forth. So you are not breaking the algorithm itself, you are breaking the physical implementation because you have physical access. Sometimes you don't have direct physical access. For instance, in cloud, we have attacks like timing attacks, but that focus on cache. So if something is cached, the result is obtained in a faster way. If it is not in the memory, it is not in the cache, it takes longer time. Again, by doing it, some people can attack Amazon services and obtain the secret information from other users because they are running the same CPU cores and so on. Okay, so this is why we will be talking about side channel analysis, what can be done in the final weeks of this lecture. Okay, so our aim is to have a lightweight algorithm that is also side channel resistant. Okay, even if you measure the power and if you perform power analysis, if you measure the power consumption, I want my algorithm to be secure at the end. That is the reason I need the lightweight cryptography. Okay, so this is why actually we are having this course. Okay, otherwise, advanced encryption standard is fantastic. We could use it everywhere. Okay, but in practice, it can be broken due to your implementation. Sometimes the device might be really small and it may not provide you enough throughput if you use advanced encryption standard. It might not have the latency you want and so on and so forth. So from the perspective of NIST is saying that use AES whenever you can. If you are not happy with it, use a lightweight algorithm. But NIST says that we don't have a lightweight standard yet. This is why we are having a competition. And I think in a few years, we will have the winner of the competition, and I will talk about it at the end. Okay, so let's look at briefly what cryptography is about, because maybe you haven't taken any cryptography course before, so we have to briefly mention what we are doing. So cryptography actually solves a lot of problems. One of them is confidentiality. We do this by encryption algorithms. We have block ciphers, stream ciphers. We have public key encryption algorithms like RSA, AlGamal, and so on. But we also have authenticated encryption algorithms. And current NIST lightweight cryptographic competition also focuses on authenticated encryption algorithms. So this is why we will be talking much about this in this course. We also provide data authentication by hash functions, message authentication codes, but also, again, authenticated encryption. Cryptography also solves the problem of entity authentication, mostly by digital signatures. But of course, we have other algorithms like zero knowledge proofs and message authentication codes. Also, it solves the problem of origin non-repudiation by using digital signatures. So we have a lot of algorithms, and actually we want all of them to work in lightweight devices. So we always want lightweight versions of this. For instance, there are many digital signature algorithms, but sometimes some of them works faster on small devices or produce smaller signatures and so on and so forth. Okay, so this is the big picture. But if you want to categorize these algorithms, sometimes we have keyless algorithms like cryptographic hash functions. Sometimes we have keyed algorithms, and we divide them into two parts, symmetric and asymmetric, or in other words, secret key or public key algorithms. In the secret key part, algorithms use the same key material for both encryption and decryption. This is why we call them the symmetric key cryptography. There are three types of algorithms in this category: block ciphers, stream ciphers, message authentication codes. So mostly we will focus on this part because we don't have time to cover all of them. But if you want to cover all of these, you can attend my applied cryptology course. Okay, so block and stream ciphers are encryption primitives, while the message authentication code is used for data and data origin authentication. This means that these are encryption algorithms, so we encrypt the plain text and obtain ciphertext. But in the message authentication code, you don't encrypt anything. You actually give your message as a plain text, but with it you also provide a small amount of data, which proves that the authenticity of the message. Okay, but all of these topics are somewhat related to each other because you can use a block cipher and turn it into a stream cipher and a message authentication code, or you can use even a block cipher as a hash function and so on. So in cryptography, these topics are somewhat related. But in the asymmetric crypto systems, different types of algorithms in asymmetric key cryptography include key agreements, encryption, and digital signature algorithms. For the key agreement algorithms, we have Diffie-Hellman and so on. For the encryption, we have RSA, AlGamal, etc. And we have many digital signature algorithms like Schnorr signatures or elliptic curve digital signatures and so on. But again, this is a huge picture, and of course we want to run all of them in lightweight devices. They are lightweight version of these algorithms. But again, since we don't have much time for all of it, we will see the standards, but we will mostly focus on authenticated encryption algorithms or block ciphers mostly. Again, for those who doesn't have a cryptography background, let me give you some of the definitions. Plain text is what you want to protect. So this might be a file in your computer. So we call it data at rest because it stays there. Or it might be a WhatsApp message or an SMS message or your voice when you are calling somebody. We call this data in transit because you're transferring it. And also we sometimes want to protect data in process. For instance, you upload your data to cloud, but you don't want the cloud service provider to read your data. So you give it in an encrypted way. So we will call it ciphertext, but we will allow them to work on it and do modifications. This can be done with homomorphic encryption, but it is beyond the concept of this talk. So plain text is what you want to protect, and the cipher or a crypto system is pair of algorithms that convert plain text to ciphertext and ciphertext back to plain text. So these algorithms should not be secret. So we, in our standards, tell everything about the algorithm, all of the details. Only thing we don't publicly announce is the secret key that we are using for this encryption and decryption process. Okay. So ciphertext is the encrypted version of the plain text, but ciphertext should appear like a random sequence because we assume that the communication channels we are using are unsecure. So we always assume that the enemy captures the ciphertext. Okay, we want to have secure communication even when the channel is unsecure. So this is what actually cryptography solves. Okay, so it can be a wired communication, it can be a wireless communication like Bluetooth, Wi-Fi, or GSM, but still we always assume that somebody is listening. And when it is Wi-Fi communication, it is easier to listen because if you have an antenna and close to the communication, then you capture the data. Okay, but we want security regardless of the situation. In the symmetric key crypto systems, you have a secret key, you use it for encryption, and same key material is also provided to the person you want to communicate, and they also use it for the decryption. Okay, so this is the main idea behind symmetric crypto systems. And we will be using most of the time block ciphers. Block ciphers operate on B-bit blocks of data. Plain text is divided into B-bit blocks. Each block is encrypted by a secret key K to produce, again, B-bit output. Output blocks form the ciphertext. So thus a block cipher and the chosen key is actually a permutation from 2 to the B elements to the 2 to the B elements. In modern cryptography, we choose block size as 64 or 128 bits, but some lightweight designs reduce it to 32 bits. As the key, we choose 128 bits or 192 or 256 bits. There is no need to use something smaller than this number, and I will mention it again. Sometimes when people talk about lightweight cryptography, they also think that the key size should be smaller, but this doesn't have to be the case. Okay. We have a very old standard, data encryption standard, which is no longer a standard, but people think that it is standard because the name says that it is a standard. For this reason, they changed the name of the algorithm and said that it is data encryption algorithm, DEA. But a lot of people doesn't know it, even until a few years ago at the web page of Microsoft, when you look at the blog post saying what is an encryption, they will give you how to encrypt a file. They will explain how to do it using this. Okay, a lot of people doesn't know it. There are many applications, many apps on the Google Play Store or Apple Store where they use this. Okay, but it is not acceptable. This was designed by IBM in 1970s. In 1976, NSA tweaked the algorithm by changing the S boxes. Block size is 64 bits. Key length is really short, 56 bits, and it consists of 16 rounds. Again, this is currently known as data encryption algorithm since it is no longer a standard. It became useless after 1990s since its short key is susceptible to brute force attack. Now that this is no longer a standard, we are using advanced encryption standard. It was designed by two Belgian, John Damon and Vincent Raymond. It was standardized in 2001 by NIST, winner of a competition called AES. There were other finalists like Serpent, Twofish, RC6, and Mars, and these algorithms are included in many popular libraries like OpenSSL and so on. This time block size increases. Key lengths are depending on your choice. If you want longer security or military grade security, you can increase the key length. But once you increase the key length, the number of runs also increases. So for instance, if you move from this key size to this key size, you lose 40% of performance. That is the trick. Okay, so with these standards, let's say why we need lightweight cryptography. Many modern cryptographic algorithms are designed for desktop computers or servers, thus they may not fit into many IoT devices, or when they did, their performance may not be as good as expected, okay? This is why we actually are talking about lightweight cryptography. In the following slides, in the next hour, I will talk about what kind of designs we have and why we have them and how the competition is going. But before moving on, let's talk about the key sizes. Some early lightweight designs have short key lengths. For instance, for this, which is not a lightweight design, but it has a 56-bit key. This means that you can have 2 to the 56 different secret keys, right? So this number is this. And in a modern GPU, you can perform a brute force attack, and in a second, you can try 2 to the 33 or 34 secret keys in a second. So trying all of these keys on a single GPU will take less than a year. So if you have a lot of GPUs, you can capture a desk key using brute force attack in a few days, okay? So once we increase it, some early lightweight designs use 80-bit key, the number increases, but again, for agencies, this number is not that big, you can still break it. And if you move on to 128-bit, the number really increases since these are exponentially increasing. And to the best of our knowledge, even if you use all of the computers, all of the computation devices in the world, performing 2 to the 128 encryptions is beyond our limits. So it will take billions of years. So the end of the universe will come most probably earlier than the time you find the key, okay? Of course, we are assuming that you can pay the electricity bill at that time. But even if somehow we reach this position, increasing the key length, you know, the number increases really exponentially, really fast. So if you are on the side of this picture, you would be secure enough. So this way you actually provide the security upper bound by choosing the key length. And nowadays NIST says that 112-bit security is enough. But maybe 10 years later, they will say that you should move on to 128. So if you are at this point, most probably, if there isn't any huge technological advancements, you will be secure enough. So it is enough to use this. So there's no need to design an algorithm that uses shorter keys, okay? And I'm focusing on this part because lightweight cryptography does not mean short keys, okay? This is the main take from this slide, okay?